Okay. So let's go and kind of do a little review here. So we have our x prime equals gamma x minus VT. Then we have y prime equals y. We had z prime equals z. Then t prime equals gamma t minus v x over c squared. Yeah. Okay, so we did a couple things here. What did we like about time? I want to write this as a 4 vector.
It's not in meters.
It's not in terms of length here. So right, because this is going to be length and this is the time. So what do we do to get it in terms of distance? We multiply this entire equation here by c. We take this one here, we multiply it by c, and this gives us ct prime equals gamma ct minus v over c, x like that. And then we write this quantity here, v over c. We define that to be beta. And range on beta is between -1 and 1. Right? Because you're going to be going c to the left. If you're going to the right, we c to the left like this, and getting the minus sign. So we have that. And so when we do this, putting this all in terms of beta, what do we have to do here in this term? I don't want that t, I want ct, so we multiply the multiplying here by c. And so this term here gives us an x prime equals gamma x minus beta ct. And we get y prime equals y, t prime equals t. I don't get that now. Z prime equals z, and then ct prime equals gamma ct minus beta x. So we look at it and say, hey, we can write this as a big matrix. So we write this as ct prime, x prime, y prime, z prime. And that equals, and then here we got, we're off, I'm not off. Ct, x, y, z like this. So what does this element have to be here? So I want you to boom, 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 boom. I want to get this equation here. This equation has to be gamma
minus
beta
gamma
0,
0
0, 0. Then we do that for all the rest, and we ended up with yes. We had that. And we said that looks good. And so we said we're going to call this here a 4 vector. So this looks like the 4x1 version of the 3x1 XYZ. So we guess that this is going to be our four-dimensional column. And so there's a problem with that. And the problem with that is this. So we can't quite say that basically that this right here is a 4 vector, since the length of this 4 vector, okay, x bar prime x bar, which is this guy, does not equal this x prime bar transpose x bar doesn't equal this guy here. So that didn't work. Okay, now daily homework 4. Okay, what did you show? You showed these two aren't quite the same, but what does equal the same when we change?
minus ct.
And when you put a minus on here, then that does work. So. But. This fellow. Does equal this. Okay, that does it equal itself. Do the same, and you did that for data homework 4. So therefore, we're going to use initial. We're going to do this historically. So historically, this was resolved using by Minkowski notation. Okay, what do we say Minkowski notation is? You just put an I with the CT. So we're going to say our real 4 vector, and again, this is going to be the Minkowski version of this, is ICT X, Y, Z. Again, no one would do this at all in the general relativity course, or even special relativity. This is not taught at all. I understand why we're not to the point of understanding why it's not done. I think it's a mistake. People should at least be exposed to it, because then if you're not, then you really can't read a lot of older literature well. And also it's just an important historically. Okay, that makes sense. So this then is conserved, and so we gave these new names. The name we gave this is, we call this X0, we call this X1, we call this X2, we call this X3. And we did a couple more things. Let's modify our matrix. So when we look at these guys, actually, let's. This. This. This one is easy to solve. We just multiplied everything by I. So I wrote this as ICT prime equals gamma ICT. And then this is going to be then minus I beta X. So I'm going to write this as a matrix. Is this first one? Oh, also, what song lyrics are you putting down?
A lot. What an audio slave.
Okay.
Yeah.
What?
Wait.
Gamma. Okay. I don't know why that just. Gamma.
I beta.
So it's going to be minus I beta gamma.
0, 0.
Then 0, 0. Now this one we have to modify. What do we have to do with this guy? I don't want CT here, I want ICT. So what do you know about that minus sign? I can write that as
I squared.
I squared. So I'm going to rewrite this guy here as gamma X plus I beta ICT. And so this becomes I beta gamma. Gamma 0, 0, and then everything else is the same. Right? And so here's our 4x4 matrix here. And in homework, you showed that was orthogonal, meaning that if we call this here A,
If the
orthogonal means that the transpose is the inverse, so A transpose times A, or the other way around, it doesn't matter. That's equal to 4x4 again.
yeah.
And then we put this all in terms of x, y, I mean in terms of 0, 1, 2, 3. And we could show that basically I can write this as using a lowercase. We write it like this. This is Greek index, and Greek indices go from where to where?
0 to 3 or 1 to 4.
0, 3, or 1, 4, and we're gonna do the 0 to 3. Like that. That makes sense? And so we're staying on the news here. Does that, anyone happy with this? We said any animal that transforms like this is a
Answer.
what kind of tensor?
First rank.
First rank. And one more first rank blank tensor.
Lorentz.
Lorentz. So this would be anything that transforms like this is a first rank Lorentz tensor. What then is a first? What is then a 0th rank Lorentz scalar?
Like equals itself.
Yes. In other words, it'd be like the when we say this fellow here. Right, that equals this quantity here. So this quantity right here, that's going to have a name in a little bit. That would be an example of a Lorentz scalar. And if I wanted a third rank Lorentz scalar, I mean, don't want that at all. If I want a third rank Lorentz vector, how would that tensor, how would that transform? Third rank. Third rank Lorentz tensor. Let's call it T prime alpha beta gamma. What would that be? Thank you.
A alpha mu.
A alpha mu.
A beta.
Mu. You know. Oh, you know that.
A gamma.
Gamma. Okay, this one. Okay, what actually do you know what comes after mu? It's not one, but I guess C. I usually avoid C, although we're going to do a proof, we're going to have C and say in the same derivation, which is evil, but traditionally everyone uses these variables. What does it look like? Something that looks like a swivel. Oh. Okay. It's like a K and an S together, like an axiom. In fact, actually, the word axiom comes from the Greek word axios, which means worthy. T. New. C. Okay. That would be a third rank tensor. That makes sense. Now, what we want to do is we want to make this look more obviously like a rotation matrix. And so we started our quest with this. And so let's make A look more obviously the rotation matrix. Let's make A, let's say more obviously look like the rotation matrix. Okay, so we have gamma, and we know that gamma is 1 over the square root of 1 minus beta squared. So what's the range on beta? I mean, gamma?
0 or 1.
0 to 2. Infinity. And we said, hey, what else has this same range?
Kosh.
Kosh. Remember Kosh. It was like this.
Oh,
And here's Kosh. The student here, this is Kosh. He's a Vorlon. This is the ship. He's an ambassador from the Vorlon Horn. And I feel it's better like him. That's an encounter too. He's actually inside them. So, and you're always very cryptic. So yes, they would say things like, "He is the closed circle. We are all Kosh." Great. An excellent science fiction show. I highly recommend this science fiction show. Besides me. So we had Kosh here. So when I say gamma is going to be by definition the Kosh, we're not going to call X, I think we call it that. We have no clue what this lambda is, but it's some Okay, then what do we say about we said that the hyperbolic tangent of x is going to be your hyperbolic sine of x of your hyperbolic cosine of x. And we said that the sinh, when we look at it, looks like this. That's your sinh. And if you do this ratio here, turns out that the hyperbolic tangent of x looks like this. So it goes from -1 to 1. So therefore we said, let's let beta equal actually the hyperbolic tangent of lambda. So we're going to let beta be by definition the hyperbolic tangent of this quantity lambda. That's actually called gamma. Here. And so the combination beta gamma is actually then your hyperbolic sine of lambda. So that means that our matrix, when we actually tinker with that, that this A here I can write as, remember that this would be cosh of lambda, because this is my gamma. This is our minus I, then beta gamma. Beta gamma is now sinh. 0, 0. And this is our I, which is sinh lambda, cosh lambda, 0, 0. Then 0, 0, 1, 0, 1, 0, 0, 0. Okay. Okay, at least we have something that has a sine and a cosine and a hyperbolic sine, so it's a little better. But we said we could do more. So we started this. You know that our cosh of x is by definition this. So we said, what happens if we let x go to minus x? You're going to let x, I should have said about x. So we have the cosh ix. This is e to the ix. Let's e to the minus of ix. 1, 2, and that's nothing but
Sine and cosine.
Cosine of x. So what I can do here, I can make use of this. So if lambda is basically some I, okay. I'm just going to say now let lambda go to some I lambda. Yeah. That means that from the cosh I lambda goes to then cosine lambda. Make sense? Okay, then we then do the sinh. So the sinh of x. How do you define the sinh of x?
With the exponential of x minus exponential of log x.
See the x minus the index x over 2. So we can do the same thing. We're going to let x go to ix. So this is the sinh of ix equals e to the ix. And I see the limits of x over 2. And this isn't quite sine of x. How come?
It's lambda.
How do we? So our sine. Where's this guy? Oh, that's your way. So our I sine of x. That.
If we just multiplied by I naught.
Yeah, so this is gonna be then I times the sine of I times the sine of x. Okay. So what happens here? So we're gonna let lambda go to I lambda. We're gonna have minus I sinh of lambda will now go to minus I sinh of I lambda. What is the sinh of I lambda? Minus I times I sine here. So this is I sine of lambda, which is S sine lambda. See what happens here is that I'm going to then with this one here, just do a minus sign. So what happens here is that this A, once we do all this, gives us what? Gives us cosine of lambda, sine of lambda, 0, 0, minus sine of lambda, cosine of lambda, 0, 0, 0, 1, 0, 0, 0, 0, 0. That looks just like a rotation matrix. Now the problem is that our angle is now imaginary because of this weird thing. So it's this weird imaginary angle. And what axes are we rotating about?
Real and imaginary.
We're somehow taking the t, the ct, and the x-axis. And we're doing some sort of rotation there about some imaginary angle. You can say, what does that mean? Exactly. So, but I mean, mathematically, it's a one-to-one correspondence. And Minkowski, I guess, from what I've read, is that he realized that actually quite rapidly. When he saw the Einstein equations, that they're just nothing but rotation matrix. Extended to 4 dimensions. But that's where you can see the idea of 4-dimensional space coming in barometrics. Okay. That's pretty cool. Now, let's get a couple more things moving here. Any questions? Okay, so when dealing with 4 vectors, instead of drawing an XY axis, we draw a CT x-axis. We always have, okay, almost invariably, not always, but almost all the time, CT is the y-axis, and the x-axis is just x. So we're going to have this, we're going to have CT here, and this is going to be x. Okay, and this is called space-time. Okay. Now again, why are we not drawing? Okay, if we had a y-axis, the y-axis would come out here. The problem is in the z-axis would be you can't draw it because it's a 4-dimensional space-time. And so we're just going to really just stick with this here and call it good. Now let's just get used to a couple things here. What would be? I want you to draw us. So we're here. We're just sitting. We're standing still. So if I were to say draw you in your chair on this axis, on this graph, where would you be?
The straight line going up.
Yeah, right, you're here, that's your position, you're not moving with time. And so what's gonna happen is that you're gonna be moving like that. Okay, if you look at a motion and the object in space-time, that's called your world line. So this is the world line. So what would happen if you're going to the right at a constant velocity? You were here,
Straight.
and now I want you to go like this. What would that be? That's gonna be something like
Straight.
this. So this is basically at a constant velocity. Suppose you're going to the left at a constant velocity. The other way. This is to the left. At constant velocity. Okay. Suppose you're going faster. So let's draw this thing. So here you are, you're stationary. This is stationary. Now you start slowly walking to the right. What would that look like?
A little bit more straight.
Yeah, it's gonna be something like that. Now you're going faster. What would that look like?
Just
Here. Okay. Could you have this?
probably not. You probably need to go at speed of light.
Okay, so the fastest you could go is the speed of light. Now, what would that look
Like just straight up parallel.
like? Okay, well, I'm gonna try to convince you that it's gonna be a line like this, and it's gonna make a 45-degree angle. Okay, this is gonna be basically one. Okay. Suppose instead my light is going to the left. That's gonna be a 45-degree angle this way. So this would be a light to the left. Now let me kind of convince you of that. So we have this guy, we have our variable here x. And this right here. Okay. I'm not gonna call that x anymore. Okay, I'm gonna actually call this s. Okay, so call this s. And what I want to do is actually just look at a differential of this. So if I want to look at ds bar, the differential of this, what would that be? I just put d's in front of things. So this would become I c dt, dx, dy, dc. Makes sense? Now, what would be then the length of this guy here? What's the length of this guy?
Very small.
Tell me how to calculate it.
You multiply it by like no, you do a dot product with itself.
Okay, so it's going to be the length of this guy. It's going to be ds transpose ds, right? Which would give me what? This is going to be minus c dt 1 to d squared, plus dx squared, plus dy squared, plus dz squared. Okay. This quantity right here is going to be, it's going to be the entire class. We don't know this yet. This quantity here is, we're going to just call ds squared. And this is going to be the space-time interval. Okay. Okay, now what's, just so you know what's gonna happen, let me just give you a preview for this class. What we're gonna find is that we're gonna wanna calculate basically the distance between 2 points in space-time. And what's gonna happen is that when we have an energy density, that's gonna change it. This is gonna really make this extremely complicated. And so what we're gonna do is that we're gonna be dealing, we're gonna love this space-time interval here because it's gonna be easy to work with. The ones we're gonna get later on, this is not one of the obvious. This is gonna be pathological. And that's where all the physics is gonna be contained. And so I'm gonna put another word in front of this soon, but not yet. I'm gonna actually call this the flat space-time interval, because this is gonna be the hallmark of flat space-time. We always get this right, but we don't have that yet. So I'm gonna pull out a d squared out of all this. So you're gonna say that my space-time interval here is I can pull out a dt squared here. And that leaves me with my c squared plus, then what do I have for this other part?
Dx squared over the
X over dt up to the squared. Plus
the dy
Oh.
over dt.
divided over t up to the squared plus dz over t up to the squared. Right? Does this have a name?
Position, the velocity
Velocity squared.
squared.
Right? So that's gonna be the velocity squared or something. Right? So this really is just gonna be nothing but the velocity squared. Now, what would happen if I had light?
It will be
What would be the light?
C.
Yeah, the light. V equals C. And so what's your space-time interval then?
0.
It's gonna be 0. Okay. So how can I write this here? I can write this in a different way. I can write this as really, and this is always true, and this is always going to be the case for light. Light will always have a space-time interval of 2. And that's going to be useful for us because periodically we're going to have really complicated space-time. We want to figure out how light moves, and so we're going to set the ds to 0.
And then when you do the dot product with yourself,
You will not be 0. You ain't light.
no.
If you're a light, you're not there. This is going to be 0. But
No.
you ain't.
I'm thinking of an angle of 90 degrees. That's I don't know where to put it because
Well, that's gonna see basically, that's gonna be, we're gonna give that a name.
like
Okay, and that's gonna be the situation where causality doesn't apply. We're not I'll rephrase that, we're not causally connected. So, we know that this is 0, so I can also write it back to our friend here. Okay, I'm not gonna worry about the y and the z components because basically I can't draw them. So let's ignore the y and the z. Y and z components. Should probably say dimension. We get that right here. And so what does that give me? This tells me that c dt squared equals dx squared. I can take the square root of this, and I can get plus or minus c dt equals dx. I take this over here. I get this, or I'll flip it. Well, what is this? This is nothing but the slope. Right? So what happens here? If I were to actually go back to that graph here, that means that light will always have, for this space here. If I have light here, so I have my flashlight here. If I shine my flashlight to the right, it's gonna go like that. This is 45 degrees. Right, because this is a slope of 1. That's just look like that. Like that. Okay, and then if I shine my flashlight going to the left, it's gonna be moving this way here, and this is gonna have, minus 45 degree angle because it's on a slope. -1. So anything that moves, let's say, where would it have to be?
In between those two.
Yeah, so in other words, if I look at just general motion, here's my light. Okay, this is actually called the light path. So what's going to happen is that everyday velocity is going to be basically contained here. So these would be everyday objects when we have constant velocities. That make sense?
Yeah. Just want to ask a simple
Sure.
question. What happens if you go past 45 degrees?
And so if you're over here, what do you do? You have a velocity
Faster than speed of light.
exceeding the speed of light. And where this is going to become important for us. I mean, from a practical point of view. So here's Jake. Here's Junior. Okay. And what I want you to do is basically I want you to communicate with lasers. So you're gonna have a laser, you're gonna shine it at Junior. As soon as Junior gets the laser, he's gonna shine it back at you. And what would that look like? So your Junior's gonna be over here, Jake's gonna be over here, and you're gonna flash shine laser beams back and forth between the two. What's it gonna look like? So first of all, what's the real line of Jake and the real line of Junior? You're both straight lines. Okay. Now, so we'll start with Jake. Jake shines a flashlight at you. What does that look like?
45 degree.
Yeah, this is going to be basically that would be this right here. Let's say you have great reflexes and you immediately get that, and then what do? You shine one back.
Yeah.
Here. Okay, and then back. And so this is how you two would communicate. That's what it would look like in this diagram. Okay. Now, this is at some point here. Okay. Here's this would be Jacob. Jacob wants to play in reindeer games too. Okay. And but Jacob wants to receive the beam at the same time as you do. So this is the time you received, remember this is CT. This is when you receive basically the signal. He wants to receive the signal at exactly the same time you do on this graph.
Okay.
How would that have to go?
You have to move to the left and then.
Well, it'd have to be basically a signal that goes like this. For Jacob to actually receive it at the same time. Is that possible?
No.
That is not possible. Okay, so what happens here is that you could have. I'm gonna have a point here A and a point here B. And there's some distance between the two here. And I call that delta S squared. Okay. So how do you calculate this delta S squared? This delta S squared would have to be minus C delta T delta T squared. What's delta X squared? Right, this would be your space-time term. Okay. There are 3 values that this can take. What are the 3 values that this delta S can take? Delta S can be positive. Delta S can be negative. And delta S can be 0. Okay. Now, the question is, can you communicate between these two points here? So let's say we take this right here. Let's say that here's point A and here's point B, and this delta S is equal to 0. Is it possible for those two people to communicate with each other? Yeah, right? If you're here, B is here, you could send a beam of light along here. And if it's equal to 0, yeah, this would be light traveling this way. That makes sense? Now, let's take this case over here. Well, this one work? Let's do this case here. Then my delta S squared be negative. If it's negative, which of these terms is winning out?
EX.
If it's negative. Which term here would have to be bigger?
Oh, the minus C.
So this term here would have to be bigger than this one here. So what does it mean here? It means that this is going to be smaller. Okay, and if we tinker with this a little bit, we'll pull out that delta T. Does this have a name?
Velocity.
This is velocity squared. Okay, so for this to be negative, what do you know about this velocity? It would have to be,
Like smaller.
it has to be smaller than c squared here for this to be negative. So what happens here? Could you communicate that?
Yeah.
Yeah, you can communicate. This is fine. This is called time-like. So that'd be a time-like space-time interval. And you can communicate between the two. But now let's say that AB here is not greater than the delta S is greater than 0. Can you communicate? To make this positive here, this would have to be greater than this. So in this case here, we have this the space-time interval is less than 0. Perfectly good. But right here, if we have the space-time interval being greater than 0, that means that V is greater than C, and you can't exceed the speed of light. Right? So if you have 2 points here, the separation distance is actually a positive space-time interval, they can't communicate. Okay? Well, then let's give a delta T and so on. Does that make sense?
Mm-hmm.
So what happens here when you have the light cone here? So this is your light cone. Like that. Communications within here, these are all possible. So this right here, all this whole region here, we're going to delta S for any space interval less than 0. But if I have a point out here, okay, this region here, and this region here, this is going to be delta S squared being greater than 0. This is called space light. Because the space is bigger. And you can't communicate there. So if you start here, you can communicate with people in this light cone. But if you're outside the light cone, you can't. Okay? Now I want to give you a little preview of what's going to happen here. Don't worry about why this is happening. We're going to spend a long time looking at why. This is just a little preview of what's going to go on. So after the break, we will look at the codes.
Yeah.
We're going to spend a long time looking at this. So here's your black hole. There's something called a short sugar radius. Don't worry about what it is. It's going to be something called an event horizon. This is going to be R here like this. Okay? And let's say you're here. This is far away. I'm going to plot C2 this way. So if I'm far away, if I look at the light cone is going to go like this. If I'm stationary, the stationary person would be here. Now let's say instead, so let's say this is home, you're with mom and dad. Mom and dad would say, you have to go do your homework. Get angry because you have to do your homework. So you hop in mom and dad's spaceship and you're gonna run away from home. So I'm gonna run to a black hole. You don't love me anymore. Okay, so you're taking your parents on a spaceship to the black hole. What we're gonna find out is that as you're moving toward the black hole here, that light cone starts shrinking up. When you get closer, it starts going like this. When you get closer, it's gonna start looking like this. So what's gonna happen here? Let's say so this is you're moving this way here. And you realize you really screwed up because you're moving toward a black hole. And so you start yelling, you start sending like a laser beacon saying help to mom and dad. Okay, when do mom and dad get this here? This one's gonna kind of go like that. And these are, as this light goes on here, this direction is gonna change because basically the light comes on again. So this one's gonna go like this, and then it kind of goes out like this. And then this one's gonna go like this. And then maybe intersect up here. And you get really, really close here, they start closing up like that. Okay. What are mom and dad gonna see? They're gonna get help, 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 help. Okay, and then eventually you're gonna have just your parents, once you get here, this thing actually closes up completely. And that light beam was just going like this. Okay, so your parents are only gonna see you basically at the edge of this. Okay. You, on the other hand, are gonna go straight through here. When it's not one bit obvious, is that light cone does something really nasty. What we're gonna see is that light cone flips. Okay. What do you have to do? You have to stay within the light cone. So can you ever communicate with mom and dad? No. Can you realize, oh no, I went through an event horizon. I screwed up. Let's put the ship in reverse. Doesn't matter. Okay, you can't get out. You're stuck. Okay, so this event horizon, I'm gonna go back over this again once we do all the mathematics, but physics of it. This is gonna be basically like a one-way membrane. Once you actually go across it, you're screwed. And this is gonna be the simple one because it's gonna be a black hole that doesn't rotate. When you get the black hole that rotates, you get a much more complicated structure. It turns out we're gonna have one. It's not really an event horizon, although it's gonna kind of look like one, but it's not. It turns out that one's not fail. If your black hole is rotating, you can go through the first one. There's a second one inside there that if you go through it, you're screwed. You can't get out. And then there's another one that occurs at the center, and it turns out that one is not going to be a surface. It's going to be actually a ring. It's going to be a singularity ring, and that one at that point, I think the physics just has to be wrong because you get something. You basically end up with a time machine. I mean, you're screwed at so many levels at that point. You can't do anything with it. But it's I think it probably needs the physics. Okay. Now, what would a time machine be? On this diagram here, what would a time machine be? Okay, what does it mean to be a time? You want to basically go in the past. Yeah. So you're here. Here we are minding your own business like this, right? We hop in a time machine here, and where do we want to go? We want to go back here. Okay, so what do you have to do? Somehow you have to go like this. That's what you have to do. Now what's going to happen here is that you're going to see that basically I'm going to try to convince you of is that if you look at the slope here, the slope is going to be related to the velocity. So these are called basically continuous continuous time loops here. They most likely don't exist. We'll find out why later on. This is basically what you do with the time machine. We're gonna have fun in class. Okay, have a good weekend.